Sorry for the late start. Now, I've uploaded the video from last class. Does anybody happen to look at it by any chance? And everybody was here, so there's really no need. But that's what I've been watching because I hate watching myself. But it'd be good to know if it's something that's actually viewable, like if writing on the board can be read. Although the one person who is most likely to complain about that has dropped a class, so so maybe it's not really an issue. Okay, and maybe I can just use this space. Okay, all right, we'll give that a go. Sometime in the next few days, maybe a weekend, I'll be making up a first Canvas quiz that'll ask questions about the concepts that I'm covering. But it's something it'll plenty of time to do because it'll feature concepts that I'm covering this week, but also next week. So I'm putting it up in advance. That'll be on material from chapter 3 in my book. So to give you a heads up, that's coming. I still have to decide which homework problems I'm going to subject you to. I have quite a collection. So don't want the assignment to be too sadistic, but at least somewhat sadistic. What? I know. Yeah, you're speaking volumes. Okay. All right. So, but I'll try to get all this sorted out and post it on the site. Certainly by next Monday. Okay. So continuing with. Actually, I have in my head which things in particular I want to cover, but I'll make sure it doesn't leave anything out. Okay, because we're going to look at matrix factorization today. Okay. All right. Come on. Okay. And also making row interchanges. All right. So. That section applies whether to my book or also the notes that are on the 610 site. Yes?
I tilt the screen forward. The top couple lines are hard to read on the video. I just pulled it up.
Oh.
That bit there, because it's really so lean back, like make it actually straight up and down.
Okay, so I like that.
But more straight up.
Then part of the board will be cut off. Okay. Wait. So.
It's like this part. You can't really tell from this, but you can't read that at all.
Oh.
The rest of it.
Yeah, they used to make it possible to enhance these videos, and I decided to take that feature out because it might be helpful. But, what? Oh. Yeah, I'm so sure Dr. Schroeder would go for that. Okay. Okay, but saying like if I make it more straight up and down, that
it might work.
Okay.
It could also be the way that the lights hit the board at that particular angle. There's just a constant glare.
Okay. Let's see. I want to move this. I also want to see if I can get away with just using this table, so I'm not moving the computer around so much. So that way I can make it more straight up and down. Okay. We'll see how this goes. Okay. Now, before I get into actual discussion of decomposition, I want to point out that a lot of entities from linear algebra can be expressed in terms of matrix multiplication, which is a key ingredient that we're going to need. So things that can be expressed in terms of matrix multiplication that aren't always, but it's a perspective that's going to be very useful to us. And really, I'm going to mention three things. Only the third one is something I'm going to need today, but I figured I'll mention all three just to ram this point home. So the first one is just an entry of a matrix. So I could say that an entry of a matrix A, I, J. So I'm going to assume that A is a general m by n matrix, m rows, n columns. So if I have an individual entry of that matrix, A, I, J, I want to work with, that can be expressed in terms of this kind of matrix vector product. EI transpose A EJ. Now, to explain all of the notation here, EI is column number I of the m by m identity matrix, and in the interest of assuming as little knowledge as possible coming into this class, the identity matrix, which we're going to see all the time, is a matrix that has ones down the diagonal and zeros everywhere else. So it's the identity element for matrix multiplication, so matrix version of the number one. So if I express the identity matrix in terms of columns, it'd be E1 is the first column that has a 1 and then all zeros. Then E2, etc., down to EM for the m by m case. All right, so in other words, EI transpose. Well, if I'm taking a transpose reverses the senses of rows and columns. So that makes it a row vector. So it has all zeros, and then a 1 in the ith position. Okay. So this EJ is a column vector, EI transpose is a row vector. So EI transpose A that's used to extract a row. So there will be certain occasions where we need to use an expression like that to refer to some row of a matrix. And similarly, J is column J of the n by n identity matrix, because A is m by n. So AEJ is used to refer to a column. All right, so multiplying on the left by a row of identity, it extracts a row. Multiplying on the right by a column extracts a column of the matrix. All right. So then you put the two together, and you get one entry. If you look at the dimensions here, EI transpose A, EJ. A is m by n. EJ is n by 1, column vector. EI transpose is 1 by m. Now remember, matrix multiplication, you're multiplying AB. The number of columns in A must match the number of rows in B. So these dimensions have to match. So the overall expression is 1 by 1. It's a number. So you're going to see this sort of thing often. So stick that in your cache in your brain now. It's a matrix entry. Any questions about that? Another thing that can be expressed using matrix multiplication that you've seen elsewhere, dot product. So if you have two vectors called u and v, normally like in a calculus class, like for us it's introducing Cal 3, u dot v, you take corresponding components, so u1, v1, u2, v2, multiply them together and add them all up. But that's the same thing as, now since we treat vectors as column vectors, that's the same as u transpose v. Now u transpose is 1 by n, v is n by 1, so the result is again a number, 1 by 1. This is also referred to as an inner product, concept that's very important, not just in this class, but other classes. Now, here, notice that the transpose sits in the middle, whereas it also makes sense to talk about, instead of u transpose v, uv transpose. The transpose is on the outside. That's called an outer product. We won't talk about that now. We will need it later. So we have the two operations that are very important not to be confused. Inner product, outer product. Because the inner product is a number. Outer product is actually a matrix. Both are quite useful. Okay. Now, the third thing I want to mention that can be expressed using matrix multiplication is one that's most important for everything else I'm going to do today. And that is, okay, well, actually maybe I'll give it a shot putting this here, see if, although, well, yeah, because right here, some pretty nasty glare.
Just draw a box around it.
Yeah, I think I'll have to.
Don't use it.
Okay.
I've had to do that before. Yeah, that spot.
All right.
Yeah.
Whoever uses this room next should be like, what's that doing there?
It'll be all right.
Okay.
I'll get you some washi tape.
All right. Is row operations that are used in Gauss elimination. So let's suppose I have a matrix A that I want to perform Gaussian elimination on. And well, for this example, I'll go with a specific size. We'll assume that A is 4 by 4. So using some examples, you guys can get the idea. So I'm going to take a matrix that is related to the identity matrix, except whatever row operation I want to do to A, I'm going to perform on the identity matrix first. So here's an example. If I take a matrix that's identity matrix, except I have swapped the second and third rows. Okay. Then, if I take that same matrix and multiply it on the left with some matrix A, the result is that I'm swapping those rows of A. So performing a row operation on A is the same as multiplying A on the left by a matrix where you performed the same operation on identity. And this is called an elementary row matrix. So it's one example of it. Because also these are referred to as elementary row operations for Gauss Elimination, so I'll go ahead in here too. Okay. Now, the operation that's of greater interest to us from last time, what we're doing, Gauss Elimination, we were taking a multiple of some row and subtracting it from another row. So I'll make up another. So what would I mean for identity? Let's suppose I'll fill in a number here, -2. Okay. So what have I done here? I've taken the second row, multiplied it by 2, and subtracted it from the third row. So if I multiply that by A, what is the result? The result is A with 2 times row 2 subtracted from row 3. Because notice rows 1, 2, and 4 are the rows of identity. So those rows in A are not touched. It's only row 3 that is affected. So when you're multiplying on the left by any matrix, the entries of that matrix indicate what is being done to the rows to make the rows of a result. So what's happening here is row 1 of a result is just 1 times the first row plus nothing times the other rows. So it's just the first row. Whereas in the third row, the interesting one, row 3 of the result is -2 times the second row plus 1 times the third row. So row 3 equals row 3 minus 2 times row 2. So that's what pre-multiplying or multiplying on the left does to a matrix. It performs manipulations on the rows. Okay. What do you think would happen if I took this matrix, instead of multiplying with A on the left, I multiplied on the right? What do you think would happen? If I multiplied A by this matrix, this exact matrix, on the right instead of the left, what do you think the action of that would be?
Switch the operations that we're doing?
Switch in what way? There is some sort of switching going on, but what exactly switches?
Row 3 is subtracted from row 2?
That's partly right.
From 2 times row 2?
There's something else that switches besides that. If you're not sure, you can try taking a stab at it.
It wouldn't just be the inverse, right?
Well, that's it. So I'd be careful not to give too much away here. Yeah.
Broken.
Okay. Well, all Alright, so instead of telling you what?
It will be the same, but the negative 2 should be 4. It's like
He said the negative 2 would be 4.
No. Well, the thing is, I'm not going to change this. I just want to know what it does to A. That's different. Okay. I'm going to do an example involving a different operation. Instead of subtracting a row from another row, I'm going to do the operation of scaling a row, because that also can be expressed using an elementary row matrix. And then I'll bet you'll be able to tell me what will happen with this case. So I'm going to make a matrix. We'll just do a 3x3 example. So I'm filling some actual numbers here. Well, I'll make boring numbers. I'm too lazy to choose interesting ones. Okay. So I'm making a matrix that. Alright. So pre-multiplying, this will scale the second row by 4. Leave the first and third rows alone. Okay, so minus 16, 20, minus 24. So now, we'll have the same A. Now you may have to go through the actual matrix multiplication process, although there's a lot of zeros here, so that helps. Okay.
Oh, the 16, 20, and 24 is transpose. What she said.
Well, okay.
Inverse transpose.
No.
Transpose.
Well, okay. Can you describe in words what this matrix will do to this one by multiplying on the right? What about it will change?
The rows become columns.
Okay, well, what?
rows become.
Yeah, the rows become the columns.
So, all right. So, in practical terms, for this example, what does that mean? Like, what?
Rotates it 90 degrees.
Okay. Like here I could say
It's not wrong.
the second row got multiplied by 4 up here.
Uh-huh.
So here, the what got multiplied by what? Describe it in those terms.
Okay. The second column will
Okay.
get multiplied by the second row. The first row.
Oh, you were so close.
The second column by the second column. I don't know. My brain's dead.
And I'm sure everybody's is. No, it's acting on columns, not rows, when you multiply on the right. So the second column has what done to it? Yes. So the first and third columns will stay the same. And yeah, so then we have
changing the row, you're changing the column.
bingo. Yeah. Okay. Yeah. So multiplying on the left affects rows, multiplying on the right affects columns. Okay.
I'm writing that down. Better be a question on the
So-
quiz.
What?
Could you repeat that, please?
Okay, so multiplying on the left performs operations on rows. Multiplying on the right perform operations on columns. So now, if we go back to the example I had over here, be careful now that he describes specifically what columns will be affected and in what way.
Third column?
No.
Second.
Second column is one that gets affected. And here's why. Because notice the third column of this matrix is the third column of identity. So that's why, whereas multiplying the left, every row is a row of identity except the third. So third row gets affected by multiplying the left. Second column gets affected by multiplying on the right. And affected in what way? What? Oh.
Said multiplied by -2.
What gets multiplied by -2?
Numbers.
What?
Second column.
No.
That would be
Row 3. Column 3.
Yes. Column 3 gets multiplied by -2 and added to column 2.
See, I thought about saying added.
Okay. Or you can take it away. Yeah, so column 2 has 2 times column 3 subtracted from it. Yeah. Okay. Pretty freaky, huh? All right. Definitely was more time than I planned to spend on this, but then again, it doesn't really matter. So, okay. So, any questions about what happened here? Everybody's brains are dead. Okay. All right. So, when I'm performing Gaussian elimination, I can express all the operations that are performed, like multiplying some row by some number, subtracting it from another row, in terms of elementary row matrices like these. And so from now on, we're just going to revert to just multiplying on the left. Okay, so what ends up happening is, because Gaussian elimination is a sequence of carefully chosen row operations to reduce the given matrix to upper triangular form, we can express that sequence of row operations as multiplying the original A by a sequence of these elementary row matrices. So, all right, so what ends up happening is, I want to write this in terms of matrix products. So I start with A, and what I want to do, now remember how I described Gaussian elimination last time. I am beginning with the first column and eliminating all the entries below the diagonal in that column. So I'll write this as E3, 1 up to En1. And the idea is Eij performs this row operation. It subtracts some multiplier times row j from row I, where I has to be strictly greater than j because we're only eliminating entries below the diagonal. So what I described here works on the first column, eliminates all the entries below the diagonal. And it has to be written in this order because in the algorithm of Gaussian elimination, we multiply first by this matrix to get rid of a 2-1 entry, then the 3-1. We keep multiplying on the left. So that's why I'm writing it this way. So now that I've worked on the first column, then I move to the second one. And I eliminate entry 3-2, 4-2, and so on, down to N2. And I keep going until I eliminate the very last entry, which is in row N, column N-1. So I multiply by all those matrices. Now, fortunately, these are very simple matrices. They're all identity with a slight change to it. So that multiplication can be carried out very effectively, or efficiently. And what's left? I have some matrix that I'll call U, which is a result of Gaussian elimination, it has an upper triangular form. Now, normally Gaussian elimination, it's a good idea to do row interchanges, but for now we're assuming that there's no need to do that. I'll talk about that later. So this is how Gaussian elimination can be described in terms of matrix products. That I start with my original A and I keep multiplying whatever I have on the left with these elementary row matrices. The result is over triangular. So like E31, remember matrix multiplication is not commutative, but it is associative. So this matrix is what you get when you've already eliminated the 2-1 entry. So that matrix has changed somewhat. And now E31 is applied to that. Then E41 would be applied to this, and so on. It just keeps cascading like that because of the associativity. Okay. So I want to use this knowledge of Gauss elimination in terms of matrix products to understand. So understanding it that way is going to lead to what's called a matrix factorization. But that only comes from seeing what the cumulative effect of all these matrices actually is. So in order to understand the cumulative effect, we need to understand each one of these matrices individually. So that I can tell you. So each matrix, Eij, has this form. It's the identity matrix. 0 is up above. And then one other change is that in column J, row I, we have this quantity here, minus Mij. Now, Mij, from the algorithm I gave last time, that's the multiplier. That's what you multiply row J by before subtracting it from row I. Subtracting it is why we have a minus here. Okay. So, and everything else in this matrix is 0. So it has a nice, fairly simple structure. Just like the example I had over there. Okay. Now, there's a lot of matrices to deal with, so I want to try to condense this a little bit. So I need to find a matrix, call it MJ. And that would be equal to a product. Okay. So I start with EJ plus 1J, J plus 2J, all the way down to ENJ. In other words, it's all the work being done on column J. So that's the job of, it's MJ's job. It eliminates all the subdiagonal entries in column J. And subdiagonal, because notice I start with J plus 1, and I go all the way to the bottom. Okay. So, MJ is a product of matrices like this. And it turns out because these matrices have such a nice structure that its identity with one entry changed, it's very easy to write down what MJ looks like. So it is, again, identity. Put the 1 down here. And it has all the multipliers in column J. So it's almost like you're superimposing these matrices on top of each other, and this is the result. And everything else is 0. Okay. both types of matrices, the EIJ here and the MJ, have a nice structure to them. We call it unit lower triangular. Now, I mentioned lower triangular and upper triangular matrices before. So a lower triangular matrix would have everything above a diagonal 0, like both of these do. Unit lower triangular, so for unit lower triangular matrix, the entries are 0 if I is strictly less than j, so that's lower triangular by itself. And all the diagonal entries are equal to 1. So that's where the unit part comes from. And anyway, that's what we see here. All the diagonal entries in both cases are 1. Now, I have my lazy notation for this too. So in lower triangular, I have a lower triangle like this. So I put a little 1 here to indicate unit. So that's my shorthand for unit lower triangular because I don't feel like writing it out. So there's such a thing as unit upper triangular too, but we'll never ever use it. Okay. Now, in both cases, we have products of unit lower triangular matrices. So there's certain properties of triangular matrices, upper and lower, and also unit triangular matrices have that are very helpful to us. Okay. That is, when you're multiplying or inverting these kind of matrices, but whatever triangularity properties you have, or unit or not, is preserved. So I'll write this using my shorthand. Upper triangular times upper triangular is upper triangular. So triangularity is preserved by multiplication. Similarly, lower triangular times lower triangular is lower triangular. Okay. And if you're not convinced, you can try it on an example and get an idea why, or something that can be proved. Debating whether to keep it as a homework problem, but that was pretty dang tedious. Second, if they're invertible, the inverse of a lower triangular matrix is lower triangular. Same for an upper triangular matrix. So inversion preserves triangularity, assuming a matrix is invertible in the first place. Now, if it is unit triangular of either kind, we'll focus on lower. Again, we have preservation of these properties. So unit lower triangular times unit lower triangular is unit lower triangular. So in other words, the diagonal entries are still 1 in the product. And finally, the inverse of a unit lower triangular matrix is unit lower triangular. Now, a unit lower triangular matrix is guaranteed to have an inverse because all the diagonal entries are 1. Because when you take the inverse of a triangular matrix, the diagonal entries are just the reciprocals. So that means they need to be non-zero, but in the unit case, they're 1. Okay. So, and we saw this property here because MJ is a product of a bunch of unit lower triangular matrices. Turns out to be unit lower triangular itself. But this property, that the inverse preserves this property, is going to be very useful to us too. So now that I'm expressing Gaussian elimination in terms of what is done one column at a time instead of one entry at a time, that's very cumbersome. That'll get us closer to arriving at a factorization. Sorry. So I can have a computer straighter. Okay.
What? I'm here to help.
What?
But I'm here to help.
Okay, good. So I have A multiplied on the left by M1, M2, up to N minus 1 is this upper triangular matrix here. So now what I can do is each of these is invertible. It's unit lower triangular. So I can multiply on the left by the inverses of these. So for example, if I multiply on the left by first matrix, Mn minus 1's inverse, these cancel out. So now I move that one to the other side. And then I can keep going. I can multiply on the left by Mn minus 2 inverse, cancel it out. Okay. So now we're seeing an accumulation of these matrices on the other side in the opposite order from before. So I keep going, and I end up with this. A is equal to M1 inverse, M2 inverse, Mn minus 1 inverse, U. Now, let's see. What about the inverse of these? So I know what the individual matrices, M1, M2, etc. look like. I wrote it down over there. But it turns out the inverses of these are known. So MJ inverse, in fact, is almost exactly the same as MJ. I have ones down a diagonal, because unit lower triangular, and I have the multipliers again. The only difference is there's no minus sign. And if you were to work an example, you can convince yourself of that this matrix times the MJ over there that has a minus actually gives you identity. And because M1, M2, etc. are unit lower triangular, the inverses are unit lower triangular. So also, this product over here is unit lower triangular. So now I can say that A is factored into the product of a unit lower triangular matrix and an upper triangular matrix. So I'm going to let matrix L be equal to M1 inverse, M2 inverse, up to M minus 1 inverse. And that is a unit lower triangular matrix. Then I can say that A is equal to LU. So this is what I was trying to arrive at. That Gaussian elimination achieves factorization of A into matrices that have a nice structure. So this is called the LU decomposition, also known as the LU factorization. Okay. Now, we know what U is from last time. U is a result, the output of Gaussian elimination. That you've reduced A to upper triangular, or if you prefer, row echelon form, and that's U. L, turns out, is a matrix that has all the multipliers that were used during Gauss elimination are stored in L. So even though I expressed L as a product of inverses of elementary row matrices, turns out to actually figure out what L is in the end, we just gather all that during a Gauss elimination algorithm, because all these entries of L are computed during that algorithm anyway. So what you can do is, during a Gauss elimination algorithm, you compute a multiplier, you use it to perform a row operation, and you can store it down here in the lower triangular part of L. And then, so in fact, what we can say is it can return its output, both L and U, in one matrix for efficient storage. The idea is you store U in the upper triangular part, including a diagonal, and then all the multipliers go in the lower triangular part. So use every ounce of storage that you have. You don't need to store these once. You know that L is a unit lower triangular matrix. You know the diagonal entries are 1. There's no need to explicitly store that. So practical implementation will return the information you need, at the interesting part of L and U stuffed in one matrix, because they occupy complementary parts. Okay. Any questions about that? Now, so once Gauss elimination does this, how does that LU decomposition help us with what we're doing in the first place? And as we're solving a system of equations, AX equals B. So let's take a look at that. Because since L and U are both some kind of triangular, those kind of systems, like I mentioned last time, those are kind of easier to solve. So if I have AX is equal to B, well, A is equal to LU. So I have LUX is equal to B. So I'm going to label this vector, which I don't know, because I don't know what X is. I'm going to call it Y. So that means that LY is equal to B, and UX is equal to Y. Now, since both of these systems are triangular, we can just use substitution to solve them. So the overall process is this. To solve AX equals B, first you do A equals LU. So that is Gaussian elimination. But that part's pretty expensive. As I mentioned last time, it's roughly 2/3 n cubed floating point operations. Once you have that, you solve this system, the lower triangular system. Ly is equal to B. For that, you use forward substitution. Because the first equation is trivial to solve. You just do a division, and then you substitute that unknown into the second equation, solve, and the third equation, solve. So you keep substituting, and that is a lot cheaper. It's n squared minus n floating point operations. So it's an order of magnitude less than Gaussian elimination. And then you have the vector y, which you plug in here, and now you can solve for x. So you solve ux is equal to y, that is back substitution. And that takes n squared floating point operations. The reason for the difference between the two operations is, two algorithms, is since L is unit lower triangular, like normally in substitution you have to divide by diagonal entry, but in this case the diagonal entries are 1. Okay. Actually, I've written out the algorithm for Gaussian elimination last time. I should also write out the ones for forward and back substitution. Well, there's not as much there. Okay. But one key thing to point out here is, let's suppose you're solving a system of equations, or many system of equations, several of them in a row. Same A, but different B's. You'll have to do this once, because this doesn't involve B. You just have to repeat steps 2 and 3. And the example, the application example I gave you last time, where you're solving a PDE, and you're doing this time stepping, it was a backward Euler method, your matrix stayed the same, but right-hand side kept changing because you keep stepping through time. That's an example of that same situation, where you can just factor your matrix A once and keep reusing that factorization every time step. Now, the other thing I want to point out is, when you learn about Gaussian elimination in like Math 326 or whatever first linear algebra course, what you're taught to do is you have your matrix A and you slap on B in the right as like a extra column. It's called the augmented matrix. You do Gaussian elimination on both A and B. So this part is just a row operations on A to get U. The second step is row operations on B, and the result of that is Y. And then what you're taught to do is back substitution to finish it off. That's what this is. But by separating these stages, that allows reuse of L and U from one system to the next. So these are sort of things that you don't have to think about when you are solving problems by hand, that you do need to think about when it's a computer doing the work. Okay. Now, the algorithms for first forward substitution. So for solving Ly is equal to B, what you do is you start at the top row and go all the way down to the bottom. So I is referring to a row. And you start setting your unknown equal to the right-hand side at first. And then in the inner loop, that runs from 1 all the way to I minus 1. This is the substitution part. So what you're doing here is you're subtracting off terms corresponding to unknowns that you've previously computed. So for instance, when I is equal to 1, you don't have this part. Now, to give you the idea as to why this works, I'm going to write an example. It needs to be up lower triangular, unilower triangular. Okay, so this is an example of a unit lower triangular system. So the matrix L is this matrix. With a -1, 2, and -3. So for a first equation, there's nothing to do. You have your unknown, y1. But now, what you have to do is, for move to the second equation, you have to take that value of y1, which is 3, substitute it in here, and subtract that term from the other side. And that's what's being done right here. So it's that previously computed unknown times the corresponding matrix entry, subtract it, so it's moved to the other side. And then similar here, y3 is equal to 5 minus 2y1 minus -3y2. So this is the algorithm in action on this example. And because we only have 2 levels of nested loops instead of 3, that's why the algorithm requires order n² operations instead of n³, like Gauss Elimination did. Question about why this works? You guys are never going to have any questions all semester long, aren't you?
I'll have questions.
Okay.
Nice little deja vu.
Okay. Well, yeah, good point. All right. Back substitution, very similar. For ux is equal to y. So it's almost just this algorithm, previous algorithm backwards. We start at row n and backtrack all the way to the first row. And we have xi is equal to yi, start. You have another loop that's going to, because it's upper triangular, we'll start at I plus 1 and go all the way to n. And keep updating x. The only difference is, and I'm going to run out of room, each unknown at the end has to be divided by the diagonal entry, which was 1 in this case, but not here. That's why it requires n extra operations compared to forward substitution. I also want to point out, if you look back at your notes from last time where I wrote down the formula for matrix vector multiplication, you'll see this expression in there. So that's what's really going on, is we have implicit matrix multiplication going on. Okay. So between these 2 algorithms and the one I wrote last time for Gauss Elimination, these are algorithms that could be coded up in MATLAB to implement a program for solving AX equals B. As long as the LU decomposition actually exists, which is not, unfortunately, is not necessarily true. Even if a matrix is invertible, it does not necessarily have a LU decomposition. For example, what if the 1, 1 entry was equal to 0? You're getting a multiplier by dividing by that entry. So that's why, in some cases, row interchanges are necessary. But when it's a computer doing the work, that's not the only reason you might need to do a row interchange. No. That's related, but I could try remembering stuff from last spring. Okay, this is where I talk about pivoting.
Oh, yeah, that good.
Yeah, pivoting, which can cause fill-in.
Yes.
Now, if I look at the main step from Gauss Elimination, the one that actually performs the row operation, and it was this, Aij is equal to itself minus the multiplier times, oh wait, there should be a k. Now, so here's a problem that's unique to with a computer performing arithmetic. That is that AJK, that's some entry up above that's been previously worked on. It's been modified before. So this has it's going to be contaminated by round-off error that happens in every single, or just about every single floating point arithmetic operation. So this entry is hopefully only slightly erroneous. And it may not be a big deal, but here's how it could become a big deal. Because what if this multiplier is large? Then that error gets amplified by this multiplier. And the result of that is AIK, this entry that's being updated, is even more erroneous. So and now imagine if a matrix is large. So this effect propagates all the way through the matrix. So the entries towards in the bottom rows could be really badly thrown off. So we like to try to rein that in if we can. And this is where pivoting comes in. Now there's many different pivoting strategies out there, but I'll just mention the simplest one that is quite helpful. That is partial pivoting. And what you do in that case is you swap row J. So before you work on column J, you swap row J with some row I'll call P. Actually, I'll call it row Q, where AQJ is greater than or equal to AIJ for J going to N. In other words, if you look at that portion of a column from a diagonal to the bottom, you find the largest entry in that portion of a matrix. You find what row that's in, that's row Q, and you swap so that now it's row J. And the effect of that is that if you look at the multipliers, Mij, which are defined to be Aij over Ajj, well, if you swap so that the largest entry is in the diagonal position, then the multipliers are guaranteed to be less than or equal to 1 in absolute values. In other words, that ensures that the error from AJK is not amplified at all. In fact, it may be damped. So containing the size of multipliers is a very helpful way to numerically stabilize Gauss elimination. And this is why back in the early days of computers, by people who were uncertain about the viability of Gaussian elimination on electronic computers because they were because they could see this round-off error growing and growing, and how do you know that for certain problems it might not get out of hand? And so the funny thing is, numerical linear algebra really came to the forefront before electronic computers were invented, because before then, computer was not a gadget. Computer was a job title for a person. It was, for example, mainly the U.S. Department of Agriculture employed people as computers. They'd be sitting at desks all day long, solving systems linear equations by hand. And actually, most computers were women because women have better computational skills. So that's what a computer was back in those days. So solving system equations was already very important back then. So when electronic computers were invented, they wanted to make sure that they could handle this task. And they weren't sure if Gaussian elimination could do it. And that's also a reason why other approaches to solving systems, such as iterative methods that we'll see later, were also started to be developed around that time because of concerns about Gauss elimination. But Gauss elimination was eventually proven stable. Now, so I call this partial pivoting. That's because there's another approach to pivoting called complete pivoting. And that's where you're not just searching through the column, you're actually searching other columns as well, later columns, and you're doing row and column operations to, again, find the largest entry in the larger portion of a matrix. So that makes the multipliers even smaller. But that's expensive because you're doing more searching. That adds significant overhead. So people generally prefer partial pivoting. Complete pivoting is more stable for Gauss elimination, but people found that partial pivoting is stable enough in most cases. Okay. So, what does this mean for the actual algorithm that I laid out earlier? What does it mean for the LU decomposition if you are pivoting? Because then what happens is, instead of what I had before, I'm swapping rows, then subtracting multiples of rows from other rows, swapping again, possibly, and keep going. So that's reflected also by matrix multiplication. PI is called a permutation matrix. And I wrote one of those on the board earlier. So for example, matrix like this that swaps rows 2 and 3. So whatever rows you want to swap, like rows J and Q over there, you swap them in identity, and that's a permutation matrix. But here's the problem. We have these permutation matrices interlacing with these matrices that actually eliminate elements. So how do we get an LU factorization out of that? Now, that's discussed in my book in gory detail, which for this class we don't really need, and God, it would get ugly. But from a programming point of view, it's actually really easy to handle. Once you decide what rows you want to swap, you've been storing the multipliers up until this point. So when you're swapping the matrix you're working on, you also swap the rows of multipliers. So as long as you swap the entire row that you're dealing with, then everything works just fine. So, the final result is this. Instead of A equals LU, you have PA equals LU. And P is equal to a product of permutation matrices transpose. Now, and the reason for that is the inverse of a permutation matrix is its transpose. In other words, this is what's called an orthogonal matrix. So matrices whose rows and columns form orthogonal sets, which we'll see more of later when I get to least squares problems. So it makes the inverse trivial to compute. All I got to do is transpose it. And so P is a product of permutation matrices, which is itself a permutation matrix. So what P does is it's the cumulative effect of all row interchanges that happened during Gaussian elimination. And so that's what you can do, is you can keep track of these row interchanges as you go. Like the easiest way to do that, make a vector of all the indices, 1 to n. Every time you swap rows, swap those indices. And the final vector that you get is the reordering of the rows. So this is the LU decomposition with pivoting. Now, every invertible matrix has this decomposition. So as long as you're willing to do row interchanges, you know that decomposition will be there. Also, the LU decomposition is unique. So then what you do is you solve Ly equals PB, which makes sense because if you're performing row operations on A that include row interchanges, you're solving AX equals B, so you must perform the same row interchanges on B. So you do that, you apply the row interchanges to B, and then proceed with forward substitution as before, and then you solve UX is equal to Y, like before. No change there. Okay. So this is the default approach to solving square invertible systems linear equations. You do Gaussian elimination with pivoting, most likely partial pivoting, to get your LU decomposition. Then you do forward substitution, rearranging B if you need to, and then back substitution. So if you're just handed a system linear equation to solve, you don't really know anything about it, chances are that's the approach that you will use. In fact, in MATLAB, the command that you would use once you have A and B is x is equal to A / B. And under the hood, that is what MATLAB's / operator is doing. It's not, even though this is mathematically equivalent to A inverse B, what it's really doing is it's carrying out, literally, Gaussian elimination with partial pivoting to solve this system. Although it would check, like for instance, suppose the matrix A you gave it was already triangular, then it's not going to go through that whole process. But for a general matrix, that is what it will do. Okay. Well, I'm not out of time yet. Although I didn't give you guys a break either. Okay. I'm not going to talk about determinants because we don't really need them. That's the funny thing about numerical linear algebra versus ordinary linear algebra, is that in a regular linear algebra class, there seems to be a lot of time spent on determinants. So here's this god-awful 6x6 matrix, find a determinant. In numerical linear algebra, we don't even need to know what determinants are practically. Like, we just don't bother with them because we're performing other operations. We don't really need them to, solve a system of equations. Theoretically, you can express the solution of AX equals B using Cramer's rule, which is all determinants. That's terribly impractical. Okay, so make sure that there isn't anything else from this section of importance that I'm missing. Okay. All right. Okay. Let's see, because and so the overall complexity is roughly 2/3 n cubed floating point operations, just because of Gauss elimination. I mean, the forward and back substitution adds a relatively negligible amount of overhead to that, because they'll take only order n squared. Now, I do want to take a moment to explain now why we do this, solve a system of linear equations, instead of simply computing the inverse, like you were taught to do in your first linear algebra class, and multiplying by that, because of the work involved in getting the inverse. Okay, so because x is equal to A inverse B. If we have A inverse, we're just performing a matrix vector multiplication that would involve only order n squared operations. So I'm going to let capital B be equal to A inverse. So what that would mean is, if I multiply both sides on the left by A, I have AB is equal to identity. Now, if I write out B and identity in terms of their columns, then I have B1, B2, up to Bn. And then for identity, I referred to these vectors earlier, E1, E2, up to En. Now, this is a standard notation for the columns of identity. I'm going to be using it all the time. So it's something you'll need to remember. That so E1 is 1, followed by all zeros. E2 is 0, 1, followed by all zeros, etc. En is all zeros, 1 in the last position. So get used to that. I don't want to be halfway through semester and I mentioned E1 and someone's like, what's that? Yeah. So what?
I said that'll be my question.
Okay. Well, I'll be ready to throw something at you. Okay. Now, if I take this is a matrix equation because we have matrices on both sides. But if I take this column by column, I have this A, Bj is equal to Ej for 1n. So in other words, now I have a system of equations for each column of the inverse. That's it. I have to solve that to get each column. So here's what I can do. I can do my Gaussian elimination once. So that's roughly 2/3 n cubed operations, no different from before. But now I have to do my my forward and back substitution. Now, how much work is that? That's 2. What if I have that? Something seems off here. I may have something wrong in my operation totals. I just want to make sure about this. So I always remember something about back substitution needing n squared operations, but I think it might have been maybe it's the number of multiplications, not overall operations. Okay. Oh, no, I have n squared. Okay. Oh, all right. So between roughly n squared operations for this, n squared operations for this, so 2n squared. But I have to do this n times. So I have a total of 2n cubed. Okay, everything does work out right, as I remember. So we have a total 8/3 n cubed operations to compute the inverse, and then go ahead and use it after that. So it's a bit wasteful. And not to mention, some matrices are more difficult to work with than others. It's called ill conditioned, which is something I will cover next week. And because you're doing extra work, that's additional opportunity to accumulate round-off error. So even if you're willing to incur the extra expense, if that's not a problem for you, you're likely to get less accuracy. This is something, if you try this in MATLAB, like MATLAB, you could do inv A times B, and MATLAB's going to warn you about this, but this is just not a good way to go. So just don't do it. I mean, if you have a 2x2 matrix as a formula for the inverse, you can just go ahead and work with that, and that actually comes in handy sometimes. But otherwise, just don't. Because now I remember when I was a beginning grad student at Stanford, taking this class, our students were saying that the solution to ax equals b is a/b. All numerical methods are propaganda. All right. So, okay, well, it's 6:12. So this is what it takes in the general case, but now on Monday, I'll talk about certain classes of matrices for which the system equations can be solved in less time due to some nice properties that they have. And then I'll talk about how bad the error can get for solving systems next Wednesday. And then we'll get into stuff that's new to everybody in this room. Okay. All right. Let's grab it.